So I'm calling in today from unceded Musqueam territories, and the organizer asked me to present about state space model, and in particular how to fit state space model in an R package that's called Template Model Builder, or TMB in short. And that's what I'll try to do today. It's a bit of a daunting task because there's a lot of pieces to TMB and to state space model, but I'll try my best. Okay, so state space model are incredibly popular in ecology. They're used and have been used for decades to model population dynamics, to estimate population size, especially in fisheries. They've been used for decades also in animal movement ecology to deal with measurement error. And they've been used now to model tons of different time series in ecology. And they're used in epidemiology and in finances and in a lot of different fields. And one of the reasons why they're very popular is that they're allowed to better predict the true value of a time series. And this is a small simulation. It's actually a simulation that we'll do today in a tutorial. And what we're looking at here is the red dots are a simulated true time series, say the population size of the species that you're interested in. And then the blue are the simulated observation. And the idea is that, as it is commonly the case in ecology, you don't observe things perfectly, right? You observe things with error. So you've got the true population size, and then you got what your survey tells you the population size is. So you have your estimate. And then the idea is that if you have a good state space model and you fit that state space model to your messy observation, you hopefully get a better value of the true time series. And here, that's what we did. We fitted a state space model to this observation data, and the black line is our estimated true state, and the gray band is the 95 confidence interval. And what we see is that the black line is close to the simulated true value, so it's doing a good job, and it's definitely closer than the observation. And in addition, the 95 confidence interval cover most of the true states, right? So if you have a good state space model for your data, you can get at a better estimated of the true kind of hidden process. And that's one of the reasons why they're so popular. But what are these state space models? Well, these state space models are hierarchical models for time series. And kind of the simplest way to think about them is with these two equations, a process equation and a measurement equation. And what the process equation does is it models the state, so the underlying state, say the true population size, as a function of the state value at the previous time step. So this would be a deterministic function, and it models kind of the behavioral process. And then you have some process noise. So that's the stochasticity that allows you to not perfectly model what's happening in the population, and allows you to kind of just have noise in the background. Then we have this second equation, the measurement equation, which models your data at time t as a function of the true state. So let's say your survey of your population as a function of the true value of the time series, plus this measurement error, right? And this measurement error is the reason why we need this state space model, is that we usually think that there's biological stochasticity, plus we don't measure things perfectly. Another way to look at these two equations is through this graph, where the arrows are representing the dependency. And then the process equation is modeling the autocorrelation of our time series, right? The modeling that the true value of time series at time t is dependent on the value at the previous time step. And then our observation are assumed to be what we call conditionally independent. So they only depend on the state value at that time, and there's no temporal correlation in the observation once the autocorrelation in the process has been accounted for. One of the reasons why these state space models are so popular is that they're incredibly flexible. So the two deterministic function can have a variety of form. They can be the good old linear form, which is definitely makes things a little bit easier, but they can have, complex function within them. And the same goes for the two stochastic portion. So they can have the good old, bell-shaped curve. So you can have normal error, but you can also have a variety of other distribution, gamma, Poisson, whatever feels appropriate for your model. And so this combined flexibility and the fact that it can allow you to get a better prediction of the underlying true latent state is the reason why they're so popular. Okay, so let's maybe look at a toy example, and this is the toy example we're going to have in the tutorial just to concretize things a little bit. So this is the toy example that we use to simulate this time series. So the idea is that your, let's say your population size at time t is a function of your population, well, is your population size at the previous time step. So pretty much how many fish you have at time t is just how many fish you had at the previous time step plus some stochasticity. And here, this process noise is modeled with a normal distribution with mean 0 and with a variance, a process variance. And then the measurement equation is also very simple here, where we have our observation is just the true value of the time series plus some error. And again, the error is normally distributed with a standard deviation, which is different than the one from the process equation. And if we simulate from this model, we get this time series that we looked at the beginning. Okay, so this is a very simple example that we'll see again in the tutorial. And then I'll build up on a little bit more complex ecological example. So state space model has been used for decades in movement ecology, and in particular to model the movement of marine animals. And a lot of the early state space model were for Argos location. And the idea is that a lot of technology like GPS doesn't work underwater. And even for animals that come to the surface, it doesn't, or at least it didn't used to work very well. So people were using this alternative method called Argos that gave the location of the animal, but with a lot of error. So this is a ring seal movement track. This is Baffin Island, Canada, and this is Greenland. And it looks like it's going back and forth from Canada to Greenland in a few hours, which is clearly not possible. And it's just measurement error. So the idea here is that we're going to develop a state space model that will allow us to get a better prediction of where the animal truly is based on that very messy movement data. And the idea is that we're going to have these dependencies of where the animal is at time t is going to depend on where the animal was at the previous time step, and it's going to be close to where it was before. And we're going to think that it's going to move in kind of the same-ish direction and at the same-ish speed. And that's going to give us kind of a distribution with a probability where we think that the animal is going to be, close to here based on the movement that it was doing before. Now we're going to say based on where the animal is, where we think it's going to be modeled with, it's going to be a t distribution, which is very close to a normal distribution, which is just going to be like, we're going to observe our Argos location is going to be close to where the animal actually is, but there's still a probability to see it a little bit further away, let's say here. And then the idea is that based on our time series of observation and our two kind of probability model, we're going to be able to estimate the true location of the animal, and hopefully these estimated true location is going to be closer to the real track of the animal. Okay, so let's look at the math, and this is going to be a model that we're going to have in the tutorial again. So here our state, which is the latitude and the longitude, for example, of the animal at time t, is going to be close to where the animal was at the previous time step. And we're going to predict that the animal is going to move in the same direction at the same speed as the previous time step. So the animal at time t is going to be close to where it was before. And then we're going to, this is Cartesian coordinates. So we're going to take the difference in the x and y direction. And we're going to say we think that the animal is going to move in the same direction and the same speed, with some stochasticity, which is going to be modeled with a bivariate normal. Now, the measurement equation, and this is where things get a little bit complicated because Argos data is quite messy. One of it is that it has these huge outliers, which we saw in the track for the seal. So we're going to use a t distribution. But the other complication is that it's taken at irregular time step. So here we're taking our process equation is at regular time step. And when we get an observation, let's say at time t or at time I, we're going to say that the animal is going to be on a straight line between our two time steps. So let's say these locations are taking it at every hour and we have an observation at 45 minutes. We're going to say that, you know, the animal is going to be 3/4 of the way in its path between time t minus 1 and time t. And then we're going to add some error. And here again, and we'll see it in the tutorial, the error distribution is a little bit complex because Argos has multiple error categories, some location categories are much more precise than others, so we can account for this. And it's going to be these t distribution, which are distribution that have what we call fat tails that allow for outliers. So this model is usually used on this Argos data, which is really messy, and usually the movement that we have is just Argos data, but I was presented with a unique opportunity where I had polar bear data where we had Argos and GPS location, and GPS location is very accurate. And so I could fit the movement to the Argos data and then compare the predicted location from a model to the true location of the animal. And that's what we did. And this is actually the track we're going to work on in the tutorial. So the gray here is the Argos location. The red is the estimated true location with our state space model. And then the black circle that I just overlaid on top of it is the true location of the animals. And you can see that the state space model, for a variety of reasons, is doing very well. So the estimated location in red are very close to the GPS location, and definitely much closer than the gray locations that are all over the place. Okay, so hopefully you're convinced that, you know, state space model, when they're good, they're advantageous. And so how do we fit them to data? And that's really kind of the topic, a big topic of the tutorial today. So you can fit state space model in the frequentist and the Bayesian framework. Today, we'll focus on the frequentist framework in big part because TMB is mostly kind of used in a frequentist framework. So when we fit the model, we're estimating the parameters. For a state space model, we're estimating, we're going to maximize the marginal likelihood of the state space model. So this is just a marginal likelihood equation. And the likelihood is going to have one part of it is going to be the probability of our data, our observation y, given our states and our parameter theta. And that's the form of this distribution function is going to be dependent on our measurement equation. And then we're going to multiply that by the probability of our state given our parameters. And the form of that distribution is going to be dependent on our process equation. And then the key here is that we want to find the parameter values that maximizes our likelihood, right? A process that we call maximum likelihood estimation. The issue with state space model is that we don't have the underlying true state, right? We only have the observation. And to be able to deal with the fact that we don't have these observations, we have to integrate them all and integrate them out, right? So we do this high dimensional integral to kind of integrate out the states. And if you remember anything from maybe your calculus class many years ago, is that high dimensional integrals are like something that's just not fun to deal with. And a lot of the methodology available to fit state space model try to handle this kind of tricky thing of this high dimensional integral. So there's an analytical solution, and then there's approximation. The analytical solution is a Kalman filter. It was actually created for a space shuttle going to the moon. They're very fast, they're very exact, but the downfall is that they're only for simple model like the toy model that we looked at. And then there's different types of approximation. There's simulation, which are incredibly flexible, but the downside is that they're slow. And then there's the Laplace approximation, which is what TMB uses, which the advantage is that they're fast and semi-flexible. So definitely way more flexible than a Kalman filter. The disadvantage is that they're semi-flexible. So there are some limitation in the type of model that you can fit. So okay, so what is this Laplace approximation? I won't go too much into the detail, but the idea is that if the marginal likelihood is a well-behaved unimodal function, it can be locally approximated with a normal distribution. And so that means that the states are assumed to have this smooth distribution with one peak. It doesn't need to be exactly normal. It just needs to be close to normal at the maximum. But it does mean that we can't have categorical states or bimodal states, right? So that's the limitation of using the Laplace approximation in TMB. You can create algorithm within TMB that allows for categorical states, but that's way beyond today's tutorial. The bonus is that this approximation requires that we maximize the joint likelihood with respect to the state, so that we get, with TMB, we get the parameters and the state at the same time. Okay, so state space models are great, but they do have some problems, and so it's important to know about them, and today we'll see how to diagnose for them. So one issue is they can have problem estimating some parameters. So here I've simulated a very simple state space model that looks a lot like the toy example, except that we have a correlation parameter here, and simulated this time series 200 times and then fitted it. And what we're seeing here is in gray, the estimated parameter values for the process, the measurement equation, the correlation parameter, and the process noise. And then in blue, it's the value that's used to simulate. So if the model is doing great, then you would want to have the estimated value close to the true simulated value. And in here, we have two rows, one where the measurement error is 10 times the size of the process noise, and one where the measurement error is equal to the process noise, right? So that kind of same order of magnitude. And what we can see is that when the measurement error is really, really big compared to the process stochasticity, you have a hard time to estimate some of the parameters. So our estimated correlation value peak at 0 when the value was, I can't remember, 0.6, for example. And you might be wondering why that matters. One of the reasons is that it can affect our state estimate. So here, this is the root mean square error that kind of measure how close our estimated and simulated states are. And we can see that when, the measurement error is way, way bigger than the process equation, our estimated true location or true states are very far from those that you would get if you use the good parameters. But things are fine when it's kind of at the same order of magnitude, right? So how can we diagnose our models? So there's a few things. So one of it is that it might be a problem of identifiability. So when you maximize the likelihood, when you use MLE, the idea is that you want to find the parameter value that is associated with the highest value of the likelihood or the log likelihood. But when you have very complex model, it happens that it might be bimodal, it has multiple modes, and then there's multiple parameter value that are associated with a peak, and that makes it hard, right? And then you can have a case where it's non-identifiable, where there's a range of parameter value that gives you the same value of the likelihood. So it's impossible to maximize the likelihood, right? Because it's flat. So the first thing you can do, and we'll do it in a tutorial, is look at the likelihood profile. So look at different values of the parameter and then see what's the value of the likelihood. And if it has this like super nice one peak kind of shape, you kind of feel good and you're like, okay, that's an okay model. At least there's no obvious problem. If it looks like this, where it has two peaks or these very flat part, then you might be like, there's a problem here. Maybe I have to go back to my drawing board and change my model or get more data or something like that. The other thing we're going to look at is the posterior predictive check. And so the idea here is that we're going to fit our model to our data. And then we're gonna simulate from that model multiple times, say 200 times. And then we're gonna calculate a measure. So here a measure is the standard deviation of the observation. So we're gonna take the standard deviation of our observation that are simulated. We're gonna make a histogram. And then we're gonna compare this to the same measure on our original data. So the standard deviation of the original data set. If it's a good model, then your observed measure should fall close to the simulated one. If it's a bad model, then our observed measure is going to be kind of very far from those that are simulated. And then the last thing I'm going to talk about before jumping into the tutorial is the one step ahead residual. So we're used to residuals and looking at residual with the regression. What a residual does is it compares, it's the difference between our observation and the predicted value. Kind of classic residuals don't work with state space model because it's a time series. So what we use is these one step ahead residual where our predicted value are based on the data from the first time step to the time step just before the one you want to compare it to. That's why it's a one step ahead. And so if you have a good model, there should be no remaining autocorrelation. So if you do an autocorrelation function for a good model, there will be no autocorrelation. For a bad model, one of the things that could happen is that there's remaining autocorrelation. I won't go into the details, but if you can transform these residuals in a way that makes them normally distributed if they come from a good model. And so if you look at the QQ plot or the histogram here, if you have a good model, the histogram of your residual should be normally distributed. If you have a bad model, then there's going to be a discrepancy, and you could look at that via QQ plots. Okay, that's it. So we'll go through the R tutorials for TMB, but this is based on a paper with a bunch of fantastic co-authors. And in the tutorial of the actual paper, there's also show how to fit state space model and a bunch of other R packages like Stan and Nimble. Okay, so let me just go to the tutorial. Okay, so hopefully you were all able to download the code. And let me just see the time. Okay. And so there's going to be two parts. The first part, we're going to use this toy model that I showed you, and we're going to use simulated data. And then the second part, if we get there, we're going to use the polar bear data that I show with this model for Argos data. So this is the toy model that we're going to simulate. So just the state at time t is equal to the state at the previous time step plus some error that's normally distributed. And then our observation is going to be our state at time t plus some error that's normally distributed. So the first thing we're going to do, and sorry, I'm going to jump back and forth between, and you have both of these in your, in the GitHub, you have both the HTML file and the RMD file. So the first thing we're going to do is simulate the data. So here we're going to do a time series of 200 data points. I'm going to, just create a vector. Our standard deviation for our process noise is going to be 0.1. And then we're just doing a for loop where, we simulate our state at time t, given our state at time t minus 1. So the same thing here, plus some random error. Oh, interesting. Okay. So I'm just going to run this. Sorry, I'm going to try to make this a little bit bigger. Okay. So we just simulated it. Then we can plot it. And what we're seeing is this time series. This is the true values of our time series here. And then the next step in our simulation is that we're going to simulate the observation. And again, we're going to use a standard error that's of the same order of magnitude as our process error, so 0.1. And here we're just saying that, our observation at time t are the same value as the observation as the state at time t plus some error. And there's a little bit of a shift here in terms of the time points, because for this model, we're assuming that the state at time 0, the initial state, and you need this often with state space model, is a fixed value. In this case, it's equal to 0. So we're going to simulate our observation, and we're going to plot them. And so this is the same time series, or at least something very close to the time series that I showed in my presentation. Sorry, this is where the red is the simulated true latent state. And when you have real data, you don't have those red points. And then the blue are our observation, which is what what the data that we would have and that we would want to use to fit our model. Okay, so when you fit a model in TMB, the first thing you need to do is to create a C++ file that's going to have our likelihood function. So what it's going to do is it's a function that's going to take in our data, a parameter value, and is going to return the negative log likelihood. Okay, sorry, first I jumped ahead. So first we have to load the TMB library, and then we have to create this C++ file. And I've put it in the GitHub repository. But the way that you would do this is that you would need to create an independent file. So you could go and press in RStudio this plus file and do plus C++ file. And then you could write your code in that independent file. Here we have it. Here I've already created it for you, but it's very important. You can't do it within an R Markdown file. It needs to be a separate file altogether, because C++ is a what we call a compile language, where you create a file, you compile it, and then you can call it from R in this case. Okay, so this is the C++ file, and the first thing, so section A is loading the packages. So it's just like a library in R. So here we're loading the TMB library. And then section B is just defining the function. So it's just like function in R. It just says this is the function that we're going to create. And then section C is kind of the place where one of the places that becomes very important. So you want to define your input data. And in C++ language, you have to define specifically whether it's going to be a vector, whether it's going to be a parameter, whether it's going to be numeric, that kind of stuff. So here we have a data vector, and our observation is going to be Y. The end of a line in C++ has to end with this semicolon. This part here is not necessary, but is a good thing to check your state space model. So I've added it here. So here we have a data vector indicator that's called keep, and that's associated with observation. And what that does, and we'll see it later in the code, is that when we do your one step ahead residual, it knows where to remove the data to be able to do that one step ahead residual. So this is our data. And then the second part that we need to do is specify our parameters that we're going to put in. So here we have two kind of classic parameters, the standard deviation of our process variation and the standard deviation of our observation noise. And here we're using the log. What we're inputting in the function is the log, and it's because we want to use an unconstrained optimizer, and we want to make sure that the value is positive, because standard deviation has to be positive. So we're inputting something that can come from -infinity to +infinity. And here we're going to change it. We're going to take the exponent of it. So we force the standard deviation to be positive. And then the second thing is our random effect here, or our states, right? So we're going to do a parameter vector of our states. So this is going to have the values that we're trying to predict. So this is what we input, and it's very important that we specify names that we're going to use when we go back in R, right? So you have to have exactly the same name, and C++, just like R, is a language that cares about capital letters. So you have to write it exactly the same way. So here we're going to transform the standard deviation, and that's because we want to use, again, this unconstrained optimizer. So we're going to take the exponent of it. Okay, so now we're going to start defining the negative log likelihood. So, right, we want to maximize the likelihood. The thing is that most optimizer in R minimize things. So what we're going to do is take the negative of the likelihood. So then we can minimize the negative of the likelihood to get at the maximized likelihood. And we take the log of it, and that's just the trick, because it makes it easier computationally. So the first thing that we do is that we create that object, NLL, that's going to keep track of the likelihood of the negative log likelihood. And we set it at 0, and never forget that end of line in C++. And then what we're going to do is that we're going to deal with each component of our state space model. We're going to add their contribution. So the first thing that we're going to look at is the contribution of the process equation. And that looks a lot like our simulation, right? So we're going to do a for loop that's going to go from time 1 to the time before the length, the end of the size of our Z vector. And this is something that I cannot emphasize enough, and I get tricked every time. But the thing with C++ is that it use index that starts at 0. So in R, if you want the first element of a vector, you do, Z square bracket 1. And C++, if you want the first element of your vector, it's going to be 0. So it's going to be Z here, round bracket 0. So when you do for loops, you don't do for loops that end at the size or the length of the object. You have to end just before, right? Because you have your index starts at 0. So here we start at 1, and we go until just 1 minus the size of our vector. We do a for loop, and then for each round of the loop, we calculate the probability of our state given the previous state value, our standard deviation, and then this is true because we take the log of the normal distribution, and then this minus L just adds for each loop the value to this object. So it takes at first 0, then it takes minus of this, and then for each step, it will add to this value. Okay, and then the reason why we're starting to 1 here is that, remember, I told you that we fixed the first value of the state at 0, and that's why we start at 1 rather than 0. Okay, so this section here within our for loop is also not necessary, but to fit a state space model, but it's a very good thing to do because it allows you to simulate from the model that you're fitting, and therefore allows you to do a lot of checks down the road. So all we're doing here is creating a simulation block. So we're saying that, you know, your state at time I is coming from a normal distribution that's centered on your state at the previous value plus our standard deviation. Okay, so that's the process equation. Now we have to deal with the contribution of the observation equation. So again, we do a for loop. And one thing in C++ is that for loops are very cheap. C++ runs really fast, so you don't need to worry. You can make very complex for loop and everything's fine. So again, here we have a for loop. Again, here we start from 0. So from the first element of our observation vector, and we stop just before the size of our observation. And ++1 means that you do it for each one. And then we add to our negative likelihood the contribution of the observation error. And here we're using, again, a normal distribution with our standard deviation for the observation, and our it's going to be log. True means that it's going to be log. And here we have the keep I, and that's going to be for one step ahead residual. The one step ahead of residual will know to remove, you know, to pretty much it's just to tell it this is the observation and know to remove the good observation. Okay, and then again, we have a simulation block here, which is not necessary, but it's very useful for diagnostics. Okay, so these two for loops going to calculate the contribution and get at our negative log likelihood. The last two section, or the last three sections, sorry, this section here tells you to report the standard deviation in their untransformed value. And that's because, remember, at the top, we used the values that we input into the function as the log of the standard deviation. And by default, TMB is going to return, therefore, the log value. But if you want to have directly the values that are meaningful, you can do AD report. And then we have a simulation block, which is good for diagnostics. So it says that with the simulation, we want to report both the state and the observation. And then the final thing is what we're going to return. And so we want to return the negative log likelihood, right? Because the whole goal of this function is that R is going to take it, it's going to change the value of the parameters, it's going to put in the data, and then it's going to calculate the negative log likelihood. And then the optimizer is going to find, using this function, the value of the parameters that minimize the negative log likelihood. Okay, so this is the C++ function, and which I walked you through. And then there's notes here about C++ that you can read. There's lots of text. So the next step that we need to do is that we need to compile our C++ code and load it. So let's run this. And this, if it's the first time that you run it on your computer, it might take a while. You might get some warnings. And if you did errors in terms of, like, for example, you mixed up your indices or things like that, your R session can crash. So you can, if your R session crashed, it means probably that you need to go back to your C++ file and check all of your indices and that you didn't do something funky. Okay, so hopefully that worked for you. Then the next thing we need to do is to prepare all of the elements that we're gonna put in this function. So we need to prepare our data. So our data in our C++ function was called Y, and it's also called Y in R. So here we do a list of element, and we only have Y, so that's easy. The other thing that we need to put in is the starting values of our parameters and our states. And that's just because, you know, we're optimizing, so we're minimizing the value. So the optimizer needs to start somewhere. So we put the starting value. In theory, TMB can use starting values that are very off, like a lot of people just use 0, 0, 0, and that's what we're going to use here. In practice, sometimes it's better to use values that are hopefully close to the estimated or the true value. So again, here we use a list, and again, we need to use the same name as the one in our C++ function. So here's the log of the standard deviation. The starting value is going to be 0 for the process and the observation, and then we have to do it also for the states. So here we're going to do it for a time series. We're going to put zeros, and that time series is going to be one element longer than our observation because we have this initial state at t0. Okay, so that's good. And then this here is not necessary, but it's helpful. So one thing that we can do is that if we want to fix either a parameter or fix a value of the state, so let's say you know the initial value of the time series, which is what we're going to assume here, you can state this, and that's going to help the model. So we can do a list, and the list needs to have the same name as the parameter values, and it needs to be factors. That's why it says factor. Actually, I'm just going to run it and then I'll show it to you. I think that's going to be easier. So here, what we're saying is that we know the initial value of the state. So we say NA, and it's going to take the value that we put as the initial value, and it's going to fix it as this. It's not going to try to predict it. And then for all of the other values of the time series, of the state time series, it's going to try to estimate a value. And here you can see we've given it a different value for the whole length of the time series from 1 to 200. Let's say, and it doesn't make sense here, but let's say we thought that these three values of the state should be the same. Then you could make it 1, 1, 1, and then TMB would know that you share the same estimated value across these values. So that can be very useful. For example, if we assume that the process error and the observation error were the same, we could give them the same number, and then TMB would know to estimate only one value for both. Okay, if that was confusing, then just forget about this. This is a bit of a detail. Okay, so we have our data. We have the starting values of our parameters. We have this additional thing that says, okay, we know the initial value of the time series. And we have our C++ file, which is called toy2p for 2 parameters. And then we use this function, which is kind of the key function in TMB, that's called make80fun. And that takes all of these elements and will return the negative log likelihood and the gradient of it. And then the one other thing that's very important, we want to say that the states, or Z, is the random portion, is the random effect. And that's where the Laplace approximation is going to be applied to, right? So it's going to use the Laplace approximation from the state, so it's going to integrate over those. Okay, so we're going to run this. And again, this is another place that if you have something wrong in your C++ file, or if you know your length of your observation is longer than what you specified in your loop, you might have R crashing. So if you have the little bomb of RStudio when you run this, then you go back to your data and you go back to your C++ file and see if there's a problem, particularly in the indexing. Okay. And now we've kind of created this object, and now we can maximize the log likelihood or minimize the negative log likelihood. So we're going to use NLMinB, which is just a classic optimizer in R. We're going to give it the starting values, which are going to be part of this object that we're creating. The objecting function is going to be our object $ function, and then it's also going to use the gradient. So we're going to run this, and this is the optimization. So this is what it returns. And then the first thing you want to do once you fit your model is that you want to check whether it converges. So here it has relative convergence, so it seems like it's good. Okay, so it looks like we fitted the model. So the next thing that we want to do is, okay, let's look at the results. So the first thing that we can do is we can look at our parameters. So we use, remember, SD report and in the C++ file. So we're going to take the summary of that. And then here, remember, here, remember, we've simulated the data, so we can actually compare how well our model did. So this is the simulated value for our two parameters, and this is the estimated value, and they're doing pretty good. So they're really close to one another, and the standard error is not too large. So things seems to be good. And then the next thing we can do is we can extract the states, and one way we can do this is we use this is the make ADFun object. We can find all of the value associated with our states, which is Z, and we can look at them. So this would be the start of the estimated time series. So starting at time 1, and then the standard error. And using the standard error and the normal approximation, we can create confidence intervals. I'm just going to go quickly around this, but you just find the quantiles to get at the confidence interval. And then let's plot it. So here, what we have is that this is the red is the one that we simulated. The orangey yellow is what TMB just estimated, and then the confidence interval, and we can see that it's doing a pretty good job in this case. Okay, so that's great. Now let's say that we had more than one model that we wanted to look at. So let me just show you the second model that we're gonna look at. So let's say we didn't know what was the real model of this time series, and we didn't simulated it. We might want to compare a bunch of different models. So here we're going to compare a slightly different model. So it's again our Tory model, but we have two additional parameters, beta and alpha, which says in this case it's the autocorrelation. So it says that the value of our time series at time t is close to the value of our time series at the previous time step, but not exactly that. So let's say this was 0.5, it would be like half of the value of the time series plus some error. And then for the observation, the same kind of thing. This would deal maybe for some systematic bias. Let's say our survey takes on average just half of the population size, then this alpha could also be 0.5. In our original simulation, because we didn't have these parameters, they're in essence fixed at 1. But here we're going to fit these models that are more flexible to the same time series and see how well things do. Okay. So the first thing that we need to do, and I'm not going to go you through steps, but it's create a new C++ file for this model. And it's exactly the same setup. The only thing that we change is that that we added the new parameters that we want to estimate. These we don't need to constrain, so they're just like that. And then the other thing that we do is that we need to add these parameters in our likelihood, our negative log likelihood in our simulations, right? And you can look at the details at another time. Okay. So we have our C++ file, and so we we compile it and load it. And here we do the same thing that we did before. So we put the starting value. So here we have 2 new parameters, and we create our make_AD_fun function that puts the data, the parameters, and the C++ file together. And then we're gonna minimize it. And then we're gonna look at whether it converged. So everything's good. It converged. And let's look at our results. And I'm just skipping fast here because it's pretty much the same as before. So here again, this is the value that we use to simulate it. And this is the estimated value. And again, it seems not so bad. The estimated standard deviation are close to the true one. And same thing for the beta and alpha, but the standard errors are definitely quite large here, right? So that could be indicative of an issue. If your standard error is like way bigger than your estimate, something might be a little bit off. So the main thing I wanted to show you is that you can compare a cross model with AIC. And there's some issue with using AIC with state space model, but it's an okay thing to do as a general check. So AIC has this very clear equation that relates the number of parameters as a penalty, so 2 times the number of parameters. So in the first model, we only had 2 parameters, the 2 standard deviation. And our second model, we have 4 parameters. We had the alpha and the beta in addition. And then plus 2 times the negative log likelihood, which is the thing that we actually minimize, right? So if we look at the objective, the final value, that's going to be the negative log likelihood. So we can calculate the AIC of both, and then we can compare them. And then we can see here that the AIC from our original model is smaller, although just a little bit smaller than the more flexible model. So it's smaller and it's more parsimonious since there's only 2 parameters. So you would go ahead and use this one, right? So that's good. And then the next thing we want to do, let's say you had a bunch of different models that you compare and you're happy you chose the best model. Is it a good model? So the first thing you can do is you can check the fit with simulation, which we kind of already did here because we simulated the data, but you could definitely do it in TMB without having to write your simulation in R. So here, if we want to simulate using the simulate block of TMB, we would create a list. We would create a new data object, right? Let me just show it to you. That has 0 values in it. It's just an empty, really, it's just an empty vector that we're going to put the simulated data. And then we're going to, again, use our list to set before we were using it to set the initial values before minimizing a negative log likelihood. Here we're going to use this list of parameters to set the values that we want to use for a simulation. So here, we're going to use the same values that we use for our simulation in R. And then we're going to use our make_AD_fun to, again, combine our data, which here is an empty vector, our starting values, which here are the values that we want to simulate, and our map and our random, so pretty much the same. And then here, instead of minimizing it, we're going to simulate. And here I'm using the same random seed as we used in R above, so it should give us exactly the same simulation values. And I'll let you check it later, but they're exactly the same. And so here, I'm not going to go again about comparing the simulated to the estimated value, but the thing that you could do is just use the simulation blocks. You could simulate a bunch of time and see how close your parameter values are to the simulated values and how close your true values are to the simulated value. And if you do a good job, then you have a sense that if you had perfectly modeled your data and that you're doing a good job. Okay. The next thing that we can do is use these predictive measures that I talked about, right? And that, again, will use the simulation blocks. So here we're going to simulate a time series 200 times, and we're going to take a simple measure. Here it's a trivial measure. We could have more intelligent measure, but we're going to take a simple measure of our simulated data and compare it to the one that's observed. So here, that's the number of replicate. We're setting a scenes because it's simulation. Here we're creating a matrix that's going to keep track of the measures for each of the simulations. And so the mean and the standard deviation of the observation. This is going to be the parameters we're going to use to simulate them, which would be, if you were to do this, would be the ones that you've estimated. Which is what we're doing there. And then in the for loop, so for each replicate, we're simulating using the parameters that are estimating. We simulated the y's, and then we're taking the mean and the standard deviation of the y's, and we're putting them in our matrix that we created. So since we're doing 200 replicate, we're going to have 200 means of observation and 200 standard deviation of observation. Let's run this. And this is really fast because TMB C++ is really fast. And then what we can do is then we can do a histogram, like we saw in the presentation, of those measures and compare it to the one that that we've observed with our data. So if we do this histogram here, so the histogram is the standard. This is the mean of the observation that are simulated, and this is the one that's the one from our real data. So here it looks like this model there's no obvious problem. So now let's look at an example where there are problems. So here I use the more flexible model. So you remember that model with the beta and alpha, and I didn't talk about it above, but above I use good starting values. Here I'm going to use terrible starting values. So this is the same as before, but we just use bad starting value in the more flexible model. It seems to have converged. So you might be like, okay, everything's fine. And then here, if we look at the new estimated values with this bad starting values, you can see that already that there's potentially problem, like the estimated standard deviation is 0, or the log of it is 0, which is the value that we put in. So that's kind of a bit worrisome. And definitely the alpha and beta also is 0, which is the starting value we put in. So when the optimizer gives you the starting value you put in, you might be like, something may be going on, worth checking. And then we can do some of the check that we did. So we're going to do the predictive check again, where we simulate and take a measure. So here again, the mean and the standard deviation, we're just using this new flexible model, and we're gonna plot the histogram. So it's the same as above. And then we can see here that, the simulated measures and the observed measure do not overlap at all. And so in this case, you might be going back, and in this case, you might want to try new starting values. And we know that if we use new starting values, things are going to be okay. Or in some cases, you might have to change your model and make it less flexible. Okay. So the other thing that I'm going to talk about is looking at the model assumption with residuals. And so we're going to use these one step ahead residuals. So there's this great function in TMB that's called one step predict that calculates automatically those residuals. And so here we're doing the same thing. We're doing the make a defun as before. I just rerunning it because I've run it with different starting values above. We're minimizing it again. And then once we've done these two steps, we're going to use the one step predict, where we put in our make a defun object and we specify our observation, and we specify our indicator that we saw in C++. So we called it keep. So we say, look at keep, and that's going to know where to remove the observation to be able to do the one step ahead residuals. And this is what it's going to return. So we're going to get our observations, the negative log likelihood, the gradient, the mean, and then importantly, our residuals, which is what we want to use to do diagnostic. So now that we have the residuals, there's a bunch of things that we can look at. So these, if the model is good, should be normally distributed. So we can look at our QQ plot, so with QQ norm and then QQ line, and then we can look at the autocorrelation. So there should be no remaining autocorrelation and residuals. So if we do this here with a good model, our QQ plot, right, you want the observation to fall on the line, and this is pretty good. I mean, there's some deviation here, but it's nothing too drastic, and there's no autocorrelation. So you'd be like, woohoo, things are good. The other thing that we can do is, check for consistency. And I must say this portion of TMB I don't know as well, but what it does is it checks for whether the Laplace approximation is adequate, and I do not fully know what it does under the hood, but the function is check consistency, and it takes a little bit because that's simulation based. And then the thing that you want to look at, so it returns a bunch of things, but the thing that we care about is this p-value, and here we don't want a small p-value. Here we want the data in a simulation not to be different than what we assume with the Laplace approximation. So we don't want a small p-value, and here we don't have one. We have 0.18, so it's much bigger than 0.5. So it'd be like, okay, the Laplace approximation appears to be correct. And then you also get the bias in the parameter based on the simulation, and here we can see that the bias are quite small, right? So this would be indicative of no problem. Okay, and then the other thing that we can do is look at the likelihood profile to see if there's any issue. And then again, TMB has this wonderful function called TMB profile, where you put again our object from make AD fun, which is the object that you kind of reuse all the time in TMB. And then you specify, say, the parameter you want to look at. Here, to be quick, we're just going to look at one parameter, the log SDP. All right. And then we're going to create this profile, and then we're going to plot it. And here's the negative log likelihood. So it goes down, but here it looks really nice. It has this nice unimodal shape. So you'd be happy with this, and there's definitely no obvious problem. And then as in contrast, this is going to be the likelihood profile of the model that had 4 parameters with bad starting values. And if we look at the profile of this, of the standard deviation of the process equation for this model, things are not looking as great. You can see that here it goes down, and it's super flat for a big portion of the parameter space, which would indicate parameter identifiability. So again, you know, this more flexible model with a bad starting value definitely seems to be problematic. We had multiple evidence of it. Okay, there's very little minutes left before I stop, and we haven't started the polar bear example. So I might run through it very, very, very quickly. But I won't go through the details of the model, but the code is all there. But here we're going to read the polar bear data, which is on Dryad. It's explained how you can get it. And here we have, right, these quality class, and this is what it looks like. This is the polar bear, the observed polar bear movement, and this is clearly error, but there's a bunch of different error. And because it's, you know, real data, it's in date and time format, so we're going to put in date and time. And then the key thing here that I want to point out is that because we had irregular time series, or that would be the case if you have missing data, you want to create an index that match your observation to the true states. And that's what we're doing here. I won't go into the details, but that's part of what we're doing here. In this case, the model is quite complex, so we could not estimate all of the standard error because we have multiple categories of error. So we've put some values for them, which are based on experiments. And this is just associating the good error with the good location. So that's details. Okay. And then just the part that I want to talk about briefly. So here again, we would do a C++ file, and you have it in your folder. It's the DCRW C++. So you have to create a separate file. And here in this case, our observation, so we have the same kind of thing. So we have, you know, our library, and in this case, we're using a multivariate density function and multivariate normally density function. So we use another library called density. That's going to be to use this multivariate normal distribution. And then there's a few kind of things that differ that we haven't seen before. So before we only had a data vector. Here we have a data array because it's the latitude and the longitude of the bear through time. Right, so we have an array, and then we have a matrix for the Argos categories because there's multiple parameters associated with it. And other than that, the same goes. We're going to put the parameters, we're going to transform those that needs to be constrained. The only thing that's different is we're going to use that NNL density, which is specific for the multivariate. But other than that, we're going to do the same thing. We're going to add the contribution of the process equation and then the density of the observation, and we're going to have our simulation blocks. We're running out of time, but then we're going to return the parameters and the simulations, and we're going to compile it and run it, and we're going to put in the data. We're going to put in the initial values of the parameters. We're going to create our object. That's make80fun. That's the object that we use again and again in TMB. And then we're going to fit it. And that's going to take a little bit longer. We're going to check convergence. And I'm going to just skip here while it runs because we're running out of time. So the main thing I want to show you is just that, we've looked at it with simulation, and simulations are always nice. But in this case of the polar bear example, when we do all of our tests, so when we do our predictive, when we look at the log likelihood function, they look good. So we're happy. When we look at, this is the simulated data, when we look at the predictive measures, the observed one kind of fall on the simulated one. And here it's a very small data set because it takes time to run. You could do it longer. When we do the predictive, when we do the residuals, there's no pattern in the residuals. There's no autocorrelation. The QQ plots are a little bit problematic, and you can kind of see it here that there's a deviation. So that kind of is something that we could look at. Okay, sorry, the last part was really fast, but hopefully with the simulation, you got a good understanding of how it works. There's tons of text in the tutorial, so you can go back and look into it. And with that, I'm going to stop and take some questions.
Thank you, Mahit. So anybody that has a question, please post it in the Poll Everywhere website. Jody has put the link here. So I'm gonna relay the questions that I see here from those that were most upvoted to the ones that were least upvoted. So I'm gonna start with the first one. It's focused on the package GLMM TMB. And it says, well, that package incorporates TMB without the user having to program in C++. Do you know if there are any moves afoot to do the same thing with state space modeling?
Well, you can use GLM TMB to fit some simple state space models. So you could just go ahead and do that. If you look in there's a help file which talks about the different correlation function, you can definitely go ahead and do that. I don't think there's a move ahead to do state space model, like a wrapper package for state space model in TMB, because in part the advantage of there's tons of packages that do specific things, like specific state space models in TMB. So for example, if you want animal movement state space model, you can use, foie gras or I can't remember what's the new one that Ian Johnson made, in emotion or something like that. That's a package that will allow you to fit the state space model that I showed you today in TMB, and there's other things that say if you want to do population dynamics that will have a specific subset of models, state space model that are relevant in that field. But the whole thing about TMB, how it is now, like the way that I present it, is it allows you to fit whatever state space model you want to do. It's just like JAGs or all of these tools for Bayesian work that are incredibly flexible and allow you to create the model that you want. So I guess the short answer is that there's already packages that use TMB under the hood to fit state space model, but then you're going to be restricted to the specific state space model used in that field. So if you want to create your own, then you're better to learn a little bit of C++ and do it yourself.
Mm-hmm. So the trade-off is really the flexibility against how easy it is to use, right?
Yes.
Yeah. The other question here is, can state space models help with fitting a model to a time series of abundance with many zeros due to failure to detect the organism?
Oh, absolutely. So yeah, so it's super flexible. There's no like you could use a Poisson, like let's say a Poisson distribution or a negative binomial distribution and add like a zero inflation to it. There's no limitation to that. So you just would have to, when you create your observation equation, you would have to add that inflation, but there's that would be totally fine.
Mm-hmm, mm-hmm. And then once you create your state space model, can you just use the usual predict function in R to predict new data?
I don't think so. I don't think so, no. I think though, but so like when you fit the model, it estimates the states. So in some ways it gives you predicted value, but it gives you predicted value at the time point that you've put. I'm guessing like if someone wants to predict new values for other parameter, like I'm guessing for other like sets of parameter values, I think you would have to do it via the simulation. But I don't think you can use predict. But I think you can get to predicted values, but I don't think you can use predict. But I could be wrong.
Yeah, so I'm wondering, but the simulate aspects that you added into in the code, that was just for the time periods in which you have data, right? So if somebody wanted to make predictions to the future, right, then they would have to come up with their own code, or you can trick TMB to do that for you.
If you want to predict in the future, I mean, there's always danger to predicting in the future, but you could make the state time series longer than your observation. I don't know what it would do in practice. In theory, you could. Whether that would run into optimization problems, that's another question. But in theory, you could definitely put a longer state time series than an observation time series.
Mm-hmm. Then the next question is focused on if you can include some kind of cartographic predictor covariate. So the example here is percentage of tree cover, for instance, in state space models for animal movement.
You mean like as a covariate?
Mm-hmm.
Yeah. So I mean, you would need to do like the extraction. Well, I think the easiest way would be to do the extraction outside. So would be to have covariates associated with your observations from the get-go. So you put it as data. If you want to like create a state space model that estimate the states and then based on that predict his states linked to the environmental covariates, I think you could in theory, but in practice, it would be quite challenging to code.
because that would mean that you would need to have the information from the covariates across the entire space, I would assume, right? Or
Yeah, you would need to enter like a matrix of
right.
values into TMB. And then the main issue I can think of is that I think like your state might not be like you're predicting your states under the hood to be able to link it to the underlying covariates, right? And I think it's possible, but I think it'd be hard is the answer. I
So
can't quite put all the stuff in my mind, but you would have to put the matrix in, and then you would have to have in your equation that your states link to that matrix, which I don't like, because remember your state needs to be smooth. You would have to like, yeah, link it to that matrix, get a covariates, put that covariate back into your process equation.
So,
Maybe.
so what you're saying is that it's best to run and get the states, and then once you get your best estimates of the states, then try to model that as a function of the covariates. Kind of do it two-step.
That's definitely the easiest
Yeah.
way. I mean, to be honest, like I think personally, I would use probably not TMB to do this, and I would go with a more simulation based method. So I would use maybe a Bayesian method, or I would use maybe POMP from Aaron King. So you could still use a state-based model. I just don't know. I just think it would be hard in TMB. But it might just be my limitation with TMB. So I might just more use a Monte Carlo state-based model method, where then you can simulate the states within the methodology and then match it to the underlying covariates. And I think that's very easy to do.
Mm-hmm. And so in the example that you gave, you fixed the value of the first random effect parameter, the Z1. And why did you do that? And is this necessary in order to make the OSA residuals work? Are there other strategies you might recommend if we don't want to fix the initial value?
Yeah, I mean, it's not necessary. It definitely helps in many cases. It helps the estimation. It's definitely not necessary. So then what you would have to do is then you would have to, well, you don't have to, but the one thing that you can do is that you can then create an equation for the initial state. So you would say, Z at time 0 is distributed with a normal distribution with mean blah and standard deviation, for example. And it's not uncommon to have the same standard deviation for the process equation as the standard deviation of your initial state.
Mm-hmm. But the reason you said, but why is it the case that it helps? Do you have any intuition of why fixing that first initial state is important?
It's not important. It just helps if you have it. It's just because it gives, I mean, you're having a latent state, right? So it's a time series of unknown, even if it's like 200 data points, these are, highly correlated. So in effect, you don't have that much data for a fairly complex model that you're fitting. So giving it just that little bit of information helps. It's pretty much just, it's just a helper.
Yep. So there's a question. One of the struggles I have when advising people regarding respecifying really flexible state space models in TMB is giving advice regarding the nonlinear model structures that tend to cause problems. Do you have any particular forms of nonlinearity that you discourage people to adopt because it's gonna be really hard to estimate or something?
Not on top of my head, but I mean, yes, like you can run into problem for sure. I think, no, I don't really have something on top of my head. I think in general, just like the main thing that you want to think about to me is making sure that you don't have parameters that are clearly non-identifiable. So like because the more complex your equation is, the more likely you're not going to see that, two of your parameters, for example, are always a sum of one another, for example, in which case you would not be able to estimate both, right? So when you have these more complex functions, is really to spend the time, I think, to look at each parameter and make sure that they don't come in a form that you won't be able to identify. I think often also, yeah, I think that's all I have to say with that. I think with the diagnostic, it can help figure out issues. It can, like, that's why I always start with a simulation. Like if you can't estimate it with a simulation, then there's no point to go with data, right? So like you want to check that if you simulate if you simulate the underlying model and fit it, it comes back with good parameter estimate. And then after that, you can put it to data. But yeah, no, I don't have a good answer to this question.
Yeah,
It's a great question.
I think what the person probably is referring to is these models are so flexible that it can easily create issues of generating. You can easily come up with models that result in parameters not being identifiable or weakly identifiable, and then but not necessarily realizing that this can happen or will happen, right?
Yeah. So I think, I mean, so I don't have a specific of like what shape of function is good or not good, but I think looking at the equation, checking that there's no parameters that always come in a combo function, simulated your model, fitting it, seeing that it works, and then doing all your diagnostic. And then one thing that I didn't talk about is that with regards to weak identifiability is that even if you pass all these checks with simulation, it might go wrong with your data, and that your data might, the model might not be perfect for your data. So something to do then is like, if you have issues, think about ways that you can get replicates of data. I think like the thing with state-space model is that they're very complex model for a single time series. So if you have duplicates, so sometimes if you have multiple individuals, fitting it in the same model helps with more complex models. Same thing with survey data. People often take the average of your survey in a year and then fit that average with a state-space model. You'd be better off in many cases, you'd be better off to not take the average, take the raw data from all surveys, because they're replicates, and that really can help estimate things like observation error and things like that.
Yeah. One more question is, can you have in state space models a describing the process using binomial or Poisson in TMB? I think what you had mentioned was something that you could not. Is that right? Have discrete random variables being estimated, or you can?
Oh, you can't. Yeah, I know. I mean, I think I just said Poisson earlier, but you can't. Well, you can in TMB, but so like the Laplace approximation only works on if the states are continuous and unimodal. So definitely, you don't want to use the Laplace approximation on a discrete state. This said, let's say you want to put for example, a hidden Markov model within TMB, that's possible, but then you'll have to write the algorithm for it in C++ within your function.
Mm-hmm.
And then the key thing is that it's the states that needs to be continuous, not necessarily the observation.
Right. So if the process model, if you wanted to have a model where the process is described by binomial or Poisson, then that would be complicated, right? Because then the states would be discrete, and then the Laplace approximation wouldn't work.
Mm-hmm,
Is that correct?
Mm-hmm. But I'm just thinking, I know that I've seen, yes, but I know that I've seen Poisson distribution used, but I just can't think of what's done for it to work. So yeah, but yes, no, in general, you wouldn't.
Yeah, all right. So we are already it's already 1:30 in my computer. I think this was great. I'm sorry that there are a couple of additional questions, but unfortunately we'll not be able to go over them. But I really appreciate the presentation and all the detailed code. I think it was great.